Something happened on the far side of the moon in early 2024 that almost nobody noticed, and the few people who did notice it quietly moved on without asking any questions. China's Chang'e 6 mission, one of the most technically complex lunar operations ever attempted, landed in a location that was not where it was supposed to land. Not by a little, by about 400 meters. And in the world of space exploration, where landing zones are calculated down to single-digit meters and trajectories are planned years in advance, 400 meters is not a rounding error. That is a deliberate choice. Nobody announced it. There was no press conference. There was no correction published in a scientific journal. The Chinese National Space Administration released imagery, celebrated the mission's success, and moved on. And the global space community, which typically dissects every detail of every lunar landing with obsessive precision, also moved on. Almost like everyone had silently agreed that this particular question was not worth asking out loud. But it is worth asking, because when you start pulling at this thread, you find something much stranger underneath. You find a landscape that is unlike anywhere else in the solar system. A region that has been called the most scientifically valuable real estate on the moon. A place where water ice has been confirmed to exist, where temperatures drop lower than the surface of Pluto, where ancient craters have not seen sunlight in billions of years, and where every major spacefaring nation on Earth is now racing to plant a flag before anyone else gets there. The lunar South Pole is not just a scientific curiosity, it is a strategic location. It is a resource deposit. It may be the key to whether humans can sustainably live and work beyond Earth. And right now, in one of the craters down there is a sample collection site that was moved 400 meters from where it was originally planned. And the reason has never been officially announced. So let's go find out why. And if you want to keep exploring questions like this one, the ones that fall through the cracks of official announcements and press releases, then make sure you hit subscribe before we go any further, because this is exactly the kind of thing we do here. Let's start at the beginning. Not with Chang'e 6, but with the moon itself. Because to understand why that 400-meter shift matters so much, you have to understand what makes the lunar South Pole so special. And when you actually look at the science, it is genuinely one of the most extraordinary environments ever discovered in our solar system. The moon does not spin the way the Earth does. Earth is tilted on its axis by about 23.5 degrees, which is why we have seasons. The moon, on the other hand, has an axial tilt of only about 1.5 degrees. That tiny tilt has enormous consequences. It means that sunlight hits the lunar surface at an extremely shallow angle near the poles, and inside the deep craters at the South Pole, sunlight never hits at all. These craters are called permanently shadowed regions, and they are exactly what that name suggests, permanently shadowed. Some of them have not seen a single photon of sunlight in more than 2 billion years, possibly longer. Inside these craters, temperatures fall to around -200 degrees Celsius, in some measurements even colder. That makes the floors of these craters the coldest known places in the inner solar system, colder than the surface of Pluto, colder than anything in the asteroid belt, and in environments that cold, something remarkable happens. Volatile compounds, meaning things like water, carbon dioxide, ammonia, methane, all the stuff that would normally evaporate and drift off into space, they get trapped. They freeze solid, and they stay frozen. And because nothing has disturbed these craters in billions of years, that ice just keeps accumulating, layer after layer. A geological record of ancient chemical deposits that stretches back to nearly the beginning of the solar system. In 2009, NASA crashed a rocket stage called the L-Cross Impactor into a permanently shadowed crater at the South Pole called Cabeus. The impact kicked up a plume of material from the crater floor, and NASA's trailing spacecraft flew straight through it and analyzed exactly what was in there. The results were not subtle. Water ice, confirmed, not trace amounts. Significant concentrations of water ice mixed in with the regolith, the lunar soil. And water is not just water when you are talking about space exploration. Water is rocket fuel. Water, when split into hydrogen and oxygen, is one of the most powerful chemical propellants we have ever used. And if you do not have to bring your rocket fuel from Earth, if you can manufacture it on the moon itself, Suddenly, the economics of space exploration change completely. This is the concept called in situ resource utilization. It sounds bureaucratic, but what it means is simple. Instead of bringing everything you need from home, you use what is already there. And at the lunar South Pole, what is already there is water ice, potentially billions of tons of it, distributed across dozens of permanently shadowed craters. This is why the lunar South Pole is not just scientifically interesting. It is strategically vital. Whoever gets there first and figures out how to access and use that water has an enormous advantage in every mission that comes after, whether those missions are going to the moon, to Mars, or beyond. This is not a secret. NASA knows it. The European Space Agency knows it. Russia knows it, India knows it, and China knows it better than anyone, because China's entire lunar program has been building toward this region with a patience and a methodical precision that is genuinely impressive when you lay out the timeline. Chang'e-1 launched in 2007. It was an orbiter. It mapped the moon. Chang'e-2 launched in 2010. It refined those maps. Chang'e-3 launched in 2013 and put the first Chinese lander and rover on the lunar surface. Chang'e-4 launched in 2018 and did something no nation had ever done before. It landed on the far side of the moon. Not the near side that we see from Earth. The far side. The side that always faces away. The side that requires a relay satellite in lunar orbit just to communicate with, because you have no direct line of sight to Earth from the far side surface. That mission was extraordinarily complex, and it worked. Chang'e-5 launched in 2020 and returned lunar samples to Earth for the first time since the Soviet Luna 24 mission in 1976. These were samples from a region called Mons Rumker, and the analysis of those samples has already rewritten parts of what we thought we knew about the moon's geological history. And then came Chang'e-6, which was not originally supposed to be a sample return mission at all. Chang'e-6 was originally designed as a backup to Chang'e-5. If Chang'e-5 had failed, Chang'e-6 would have been retasked to complete the mission. But Chang'e-5 succeeded. So what do you do with a fully built spacecraft that is now spare hardware? You redesign the mission. You send it somewhere far more ambitious. And the target they chose was the South Pole Aitken Basin on the far side of the moon. Specifically, a crater inside that basin called Apollo Crater. And here is where the story gets interesting. The South Pole Aitken Basin is not just any crater. It is the largest confirmed impact crater in the entire solar system. Let that settle for a second. The largest. It stretches approximately 2,500 kilometers across. Its depth in some places reaches 8 kilometers below the surrounding terrain. It was created by an impact so violent that it punched all the way through the lunar crust and may have exposed material from the moon's mantle, the layer below the crust that is normally inaccessible. Scientists have been desperate to get samples from this basin for decades because what is down there could tell us things about the moon's interior that we simply cannot learn any other way. It could also tell us things about the early solar system, about the period called the Late Heavy Bombardment, when the inner solar system was being pelted with massive impactors. The South Pole Aitken Basin may be a direct record of one of those ancient collisions. And within this basin, the Chinese mission planners chose Apollo Crater as their landing zone. It is a large crater inside the larger basin, and within Apollo Crater, they identified a specific target area based on orbital imagery and slope analysis and safety considerations. That target area was published in scientific planning documents. It was the planned landing site. And then the spacecraft landed 400 meters away from it. Now let us talk about what 400 meters actually means in this context, because I think the casual framing of it as a minor deviation undersells what is really going on here. Modern spacecraft do not miss by 400 meters accidentally. The Perseverance rover, which landed on Mars, used an advanced landing system called terrain relative navigation, which essentially allows the spacecraft to look at the ground below it during descent, compare what it sees to maps stored in its computer, and steer itself to avoid hazards in real time. It landed within about 2 kilometers of its target on another planet. On the Moon, where the distances are far shorter and the technology is equally sophisticated, a 400-meter shift is not a navigation error. It is a decision. The question is, What drove that decision? And here is where the officially announced information runs dry. China announced a successful landing. China announced successful sample collection. China announced successful liftoff from the lunar surface, which is itself an extraordinary technical achievement that only the United States had done before, from a robotic spacecraft. And then Chang'e 6 returned to Earth with approximately 1.9 kilograms of lunar material from the far side of the Moon. A world first. A genuine historic achievement. But the shift in landing location? Nothing. No explanation. Not from official channels. So the scientific community, the observational community, and anyone paying close enough attention, was left to reason through it themselves. And when you start looking at what we actually know about that terrain, several possibilities emerge. And each one of them reveals something different and important about what China may have found, or may have been trying to avoid, or may have been trying to reach. The first possibility is the most straightforward: terrain hazards. The lunar surface is not smooth. It is covered in boulders, craters, slopes, and surface textures that can make landing extremely dangerous. During the descent phase, the spacecraft's onboard systems are analyzing the terrain in real time. If those systems detected a hazard at the original target that had not been visible in orbital imagery, the spacecraft would have been commanded to move. This is standard autonomous landing logic. The spacecraft finds a safer spot, it lands there, and the mission succeeds. But here is the problem with that explanation. If it were simply a hazard avoidance maneuver, it would be easy and sensible to announce that. Hazard avoidance during final descent is not embarrassing. It is evidence that your autonomous systems work. It is a technological success story that you would want to publicize. The fact that no such explanation was offered suggests either that the shift was not due to standard hazard avoidance, or that the reason behind it is something that the mission planners did not want to discuss in detail. The second possibility is that the original landing site turned out to have less scientifically valuable material than anticipated. Orbital data has limits. Spectroscopic analysis from orbit can tell you a great deal about surface composition, but it cannot tell you everything. The resolution of orbital cameras and spectrometers means that what looks promising from 100 kilometers above can look very different when you are 20 meters from the surface and descending. If the original target showed signs during descent of being less rich in the minerals or materials the mission was designed to collect, the logical response would be to shift to an area that looked more promising. But again, if that were the case, you would expect some acknowledgement of it, some scientific justification offered to the community. The silence is strange. The third possibility is the one that gets genuinely fascinating, and it connects directly to the water ice question that runs through this entire story. There has been significant scientific debate about whether permanently shadowed regions or areas with enhanced volatile deposits might exist in unexpected locations around the South Pole adjacent regions of the Moon. Not just in the deep South Pole craters themselves, but in smaller shadowed pockets, permanently shadowed microenvironments that exist at latitudes that were not traditionally considered part of the permanently shadowed region network. The South Pole Aitken Basin, because of its enormous depth, creates its own shadowing dynamics. The walls of the basin can shadow the floor in ways that do not follow the same logic as the well-mapped South Pole craters. And within Apollo crater there may be micro-shadowed regions with elevated concentrations of volatiles that were not fully characterized before the mission launched. Is it possible that during the descent phase, or based on updated analysis of the landing zone in the final weeks before landing, the Chinese mission planners identified a more volatile-rich area 400 meters from the original target, and chose to land there because the scientific payoff would be higher? And then chose not to announce the reason because announcing it would essentially be announcing coordinates of high-value resource locations in a region where every spacefaring nation is competing for position? That is speculative. But it is not irrational speculation. It is the kind of reasoning that follows from the strategic context of what is happening at the lunar South Pole right now. Because the competition for the lunar South Pole is not just scientific anymore. It has become one of the defining geopolitical contests of the 21st century, and the stakes are higher than almost anyone in the mainstream conversation acknowledges. Let us zoom out for a moment and look at the big picture. In 2020, NASA announced the Artemis Accords, These are a set of bilateral agreements between the United States and partner nations that establish norms of behavior in space, including the concept of safety zones around lunar operations, meaning areas around active lunar stations, or extraction sites where other parties agree not to interfere. The accords are not international law. They are not a treaty. They are essentially a collection of handshake agreements between nations that NASA has brought into its coalition. As of now, more than 40 countries have signed. China has not signed. Russia has not signed. China and Russia have their own competing framework called the International Lunar Research Station, or ILRS. This is a plan to build a joint crewed base at the lunar South Pole by the 2030s. And while the political relationship between China and Russia in space has had its complications, the fundamental challenge that the ILRS poses to the Artemis coalition is real, and it is documented. Both programs want to be at the lunar South Pole. Both programs want access to the water ice. Both programs understand that whoever establishes operational infrastructure in the best locations first will have a significant structural advantage over whoever arrives later. And there are only so many prime locations. The permanently shadowed craters are not infinite. The best landing zones, the ones with relatively flat terrain adjacent to confirmed water ice deposits, and also accessible to sunlight for solar power generation, are limited in number. And every mission that goes to the lunar South Pole, whether it is robotic or crewed, is gathering data that helps prioritize which specific locations are most valuable. In that context, the question of where exactly a spacecraft landed and why it shifted from its announced target takes on a different character entirely. It is no longer just a technical detail. It is potentially a piece of information with strategic value. And if the shift in landing location was driven by the identification of a particularly resource-rich spot, then the coordinates of that spot and the reason for the shift are not just scientific data, they are intelligence. This is not unprecedented in the history of exploration. When European powers were charting coastlines and mapping resources in the age of exploration, the most valuable maps were kept secret. Cartographers who worked for the Portuguese crown were sworn to secrecy. The locations of gold deposits, fresh water sources, and safe harbors were state secrets. We are in an analogous moment now. The moon is being mapped with the kind of detail that reveals resource locations, and the nations doing that mapping are not sharing everything they find. China's lunar program has been notably secretive about certain categories of data. Chang'e 4, which landed in Von Karman crater on the far side in 2019, returned extraordinary data about the subsurface composition of that region. Some of that data was shared with the international scientific community. Some of it was published in prestigious journals. But the timeline of publication was controlled. The selection of what to share and what to hold back was controlled. And no one outside the Chinese program has complete access to all of the raw data. The same is likely true of Chang'e 6. The 1.9 kilograms of far-side samples are currently under analysis. Some results will be published. But the full picture of what was found, where exactly it was found, and what the surface environment looked like at the landing site in fine detail, that picture will be assembled and released according to decisions made by the Chinese space program and the scientists working within it. And those decisions will be influenced by factors that go beyond pure scientific openness. Now, let us talk about what we actually know scientifically about the Apollo crater landing site, because there is genuinely fascinating stuff here that gets overshadowed by the geopolitical framing. Apollo crater has a diameter of about 492 kilometers. It sits inside the South Pole Aitken Basin, and it has its own complex internal geology. The floor of Apollo crater shows signs of ancient volcanic activity. There are patches of mare basalt, the same dark volcanic rock that covers the visible lunar seas on the near side. But these volcanic deposits are unusual because they are inside one of the oldest and deepest impact craters on the moon. The presence of volcanic material here suggests that even after the catastrophic impact that created the South Pole Aitken Basin, the moon's interior was still active enough to push magma up through the damaged crust and onto the surface. The samples returned by Chang'e 6 from this location should, in theory, contain both ancient impact melt material from the original basin-forming event and younger volcanic material from subsequent eruptions. If the analysis of these samples can untangle those two components, we may be able to date the South Pole Aitken Basin impact itself with much greater precision than current estimates allow. Right now, estimates for the age of the basin range from about 4.1 billion to 4.3 billion years ago. Getting a more precise date matters enormously because it helps us understand the timeline of the late heavy bombardment and the conditions under which early Earth was forming. What was happening to Earth at the same time the Moon was being hit with these massive impactors? The two bodies were in the same neighborhood. The same forces were acting on both of them. Understanding what hit the Moon helps us understand what hit early Earth. But there is another layer to this. The South Pole Aitken Basin, because it is so deep and so old, may have penetrated through the lunar crust entirely. The Moon's crust averages about 50 kilometers thick on the near side and up to 70 kilometers thick on the far side. The South Pole Aitken Basin is 8 kilometers deep. That is not deep enough by itself to breach the crust, but the impact would have also heated and fractured the crust below the impact zone, potentially allowing material from the mantle to migrate upward. If the Chang'e 6 samples contain true mantle material, or even material that is strongly contaminated by mantle components, that would be the first direct sample of the lunar mantle ever analyzed on Earth. The lunar mantle, the layer that makes up the vast majority of the Moon's interior, the layer we have essentially never touched. The implications of that for our understanding of how the Moon formed, how it differentiated into its layers, and what its internal composition really is, would be profound. It would be one of the most significant sample return results in the history of planetary science. And here is the thing about the 400-meter shift. The composition of the surface is not uniform across Apollo crater. Different areas of the crater floor have different geological histories and different surface compositions. If the original landing target was in one geological unit, and the actual landing site was 400 meters away in a different geological unit, the samples returned would be from a meaningfully different geological context. The shift matters scientifically. It changes what you get. And the decision to shift, whatever drove it, had real consequences for the scientific value of the mission. Which brings us back to the core question: what drove the shift? There is one more possibility that has not been fully explored in public discussion, and it involves the specific subsurface structure of the landing zone. The Moon's surface is covered in regolith, a loose, fragmented layer of rock and dust created by billions of years of micrometeorite impacts. This layer varies in depth and composition across the surface. Underneath it is bedrock, but between the surface regolith and the solid bedrock, there can be layers of mixed material, ancient regolith that has been compressed and modified over time, and in some cases, gaps or voids created by subsurface processes. Recent analysis of data from lunar orbiters has suggested the presence of subsurface features at various locations on the Moon that are not visible at the surface. Lava tubes, large underground tunnels created by ancient volcanic flows where the outer crust cooled and solidified while molten rock continued to flow through the interior and eventually drained away, leaving hollow tunnels. These structures have been identified elsewhere on the Moon from orbital radar data, and their presence matters enormously for future lunar habitation, because a lava tube provides natural protection from cosmic radiation, micrometeorite impacts, and the extreme temperature swings of the lunar surface. If orbital or descent phase radar data from the Chang'e 6 mission identified a subsurface feature of interest near the landing zone, that would be extraordinary information. And it would also be exactly the kind of information that would not be casually announced in a press release. Is there a lava tube or a significant subsurface void somewhere in the Apollo crater landing region? We do not know. China has not said. But the possibility that subsurface reconnaissance played a role in the 400-meter shift is real, and it is consistent with the capability of the instruments on board. Chang'e 6 carried several scientific instruments. Among them was a lunar radar sounder designed to penetrate the subsurface and reveal its internal structure. This instrument was provided by the European Space Agency as part of an international collaboration on the mission. The data from that radar sounder will eventually be analyzed and published. When it is, it may provide some clarity on what the subsurface looks like at and near the landing site. But the timeline for that publication is unknown. and whether the full dataset will be shared openly or selectively is also unknown. There is something else worth examining here: the broader pattern of behavior around lunar South Pole missions from all the major players. Because China is not the only one doing things that raise questions. India's Chandrayaan-3 mission landed near the lunar South Pole in August 2023. It was a historic achievement, the first mission ever to land successfully in the South Polar region. The Vikram lander and Pragyan rover operated on the surface for about 2 weeks before the lunar night arrived, and they went silent. The rover traveled a distance of about 100 meters from the lander and conducted analysis of the surface. The results were published, and they confirmed the presence of several elements in the soil, including sulfur, which had not been directly detected at the South Pole surface before. But the mission ended before the rover could reach any of the permanently shadowed regions. It got close. It worked in the vicinity, but the actual volatile-rich shadowed regions remained unsampled. India announced plans for Chandrayaan-4, which will attempt a sample return from the South Pole region. Japan is working toward lunar South Pole operations. South Korea has a lunar orbiter, and the United States, through both NASA and commercial partners under the Commercial Lunar Payload Services Program, is sending increasing numbers of payloads toward the Moon, many of them targeted at the polar regions. In 2024, the IM-1 mission, carried by Intuitive Machines' Nova-C lander, landed near the South Pole. It actually landed at an angle, partially tipped over, because one of its landing legs caught on a surface feature during touchdown. It still managed to operate and return some data, but the off-nominal landing illustrated very clearly how difficult this terrain is. The South Pole is not a smooth, flat plain. It is a complex, cratered, boulder-strewn environment where safe landing zones are precious and limited. NASA's Artemis program, which aims to return humans to the Moon, has identified 13 potential landing regions at the lunar South Pole. Within those regions, there are specific candidate landing sites that have been evaluated for slope, lighting, terrain roughness, and proximity to permanently shadowed regions. The selection of the final landing site for the first crewed Artemis South Pole landing is still being worked through. And that selection, when it is made, will represent an enormous amount of planning and analysis and compromise between different competing factors. The point is that everyone is trying to get to the same general area. Everyone is competing for the same limited number of viable landing zones. And everyone is gathering data, some of which is shared openly, and some of which is not. In this environment, the 400-meter shift in the Chang'e 6 landing site takes on additional significance. It is a single data point, yes, but it is a data point that sits at the intersection of science, technology, strategy, and secrecy. And the absence of any official explanation for it is itself a form of information. Silence communicates something. In this case, what it communicates is that the reason for the shift is not something the Chinese space program wanted to explain. And when powerful programs with advanced capabilities choose not to explain something, the most logical interpretation is not that the answer is boring. Let us take a step back and look at what the next few years are likely to bring. Because the context in which the Chang'e 6 shift occurred is only going to become more important. China is planning Chang'e 7, which is designed to explore the lunar South Pole in detail. It will include an orbiter, a lander, a rover, and a mini-flying probe that will be able to hop into the permanently shadowed regions, which are too dangerous for a conventional lander or rover to enter. That flying mini-probe will be able to descend into the darkness of a permanently shadowed crater, analyze the surface, and return. It is an audacious design, and it is specifically designed to characterize the water ice and volatile deposits that everyone has been circling around. Chang'e 8 is planned to follow, with the goal of testing technologies needed for the International Lunar Research Station, testing the use of local resources, testing construction methods, beginning to establish a permanent foothold. And the timelines for all of this are roughly 2026 to 2030, which is exactly the same window in which NASA is attempting to land the first crew on the lunar South Pole under Artemis. The two programs are on a direct collision course in terms of timeline and geography. Both will be at the South Pole simultaneously. Both will be competing for the same resources and the same locations. The Artemis Accords, which China has not signed, include language about safety zones and the right to use resources. But they also do not include any formal exclusion mechanism. China can land wherever it chooses on the moon, under the current international legal framework rooted in the 1967 Outer Space Treaty. No nation can claim sovereignty over any part of the moon. But presence and infrastructure create facts on the ground. If China lands at the best water ice extraction site first and builds infrastructure there, the practical reality is that they are there first. International law does not have a clear mechanism for dealing with that. This is why NASA Administrator Bill Nelson and other officials have spoken openly about a space race with China at the moon. It is not hyperbole. It is an accurate description of what is happening, and the Chang'e 6 landing shift, minor as it sounds when described as a 400-meter adjustment, is a small window into the texture of that race. Every choice matters. Every location matters. And when a sophisticated program makes a choice that it does not explain, the best working assumption is that the choice was deliberate, and the silence is deliberate. There is one more dimension to this story that I want to explore, because it connects the lunar South Pole to something even larger. The reason water ice at the moon matters is not just about the moon. It is about Mars. It is about the whole architecture of how humanity expands beyond Earth. The fundamental problem with deep space exploration is energy. Getting mass off the surface of Earth and into space requires enormous amounts of energy. Rocket propellant is heavy, and every kilogram of propellant you launch from Earth is a kilogram that costs roughly tens of thousands of dollars just to get to orbit, and then more to get further. The cost of a Mars mission, under current approaches, is dominated by propellant mass. If you could refuel in space, the economics change dramatically. The concept of a propellant depot at or near the moon would allow spacecraft heading to Mars to top off their tanks before the long journey, rather than carrying all their fuel from Earth. And if that propellant is manufactured from lunar water ice, split into liquid hydrogen and liquid oxygen through electrolysis using solar power, then the whole chain of cost and complexity for Mars missions drops significantly. The moon becomes not just a destination, but a waypoint, a refueling station, an industrial base for deep space operations. This vision has been discussed for decades, but it is only now, with confirmed water ice at the South Pole and multiple programs racing to characterize and access it, that it is becoming an operational reality rather than a theoretical concept. And whoever builds the first functioning water ice extraction and propellant production system at the lunar South Pole has something extraordinarily valuable, not just for their own Mars ambitions, potentially for selling propellant to other missions. The lunar South Pole water ice is not just a scientific resource. It may become the first genuinely commercial resource in space history. This is the context in which you have to read the Chang'e 6 mission. This is the context in which a 400-meter shift in landing location becomes not a footnote but a clue. China went to the moon's far side. China landed in one of the most scientifically valuable places in the solar system. China changed its landing site by 400 meters for reasons it did not announce, and China returned samples from that unannounced location, samples that are now under analysis in laboratories that are not fully open to international scientific collaboration. And the rest of the world is watching and building their own missions, and also not sharing everything they know. The moon, which humans visited more than 50 years ago and then largely abandoned for half a century, is now the focal point of the most intense competition in the history of space exploration. Not competition for prestige, though prestige is certainly involved. Competition for resources, competition for position, competition for the infrastructure that will determine who can go further, faster, and more sustainably into the solar system. And at the center of that competition is a region of roughly 50 kilometers around the South Pole that contains confirmed water ice, extreme cold, ancient unsampled geology, and enough strategic value to drive nations to change their landing sites by 400 meters without telling anyone why. Let's think about what the scientific community has managed to piece together, working from the outside. Several researchers tracking the mission in real time noted the discrepancy between the planned and actual landing coordinates. The planned site had been identified in pre-flight documentation and in scientific literature discussing the mission's objectives. When the actual landing site coordinates were derived from the imagery released after landing, the offset was measurable, and the offset was in a direction that moved the landing site slightly closer to an area with a different spectroscopic signature in orbital data, meaning the area where Chang'e 6 actually landed had a somewhat different predicted surface composition than the original target. Was that shift intentional? Was it driven by updated surface characterization? Was it driven by real-time terrain assessment during descent? Was it a combination of factors? The community cannot say definitively, because the people who know are not talking. What we do know is that the samples returned are currently being studied. Early results from Chinese research teams have already suggested that the far-side volcanic material is compositionally distinct from near-side samples returned by Apollo and by Chang'e 5. The ages of some of the volcanic material appear to be around 2.8 billion years, which is younger than expected for this region, and adds to a growing picture of the Moon as a geologically active world for much longer than previously believed. This matters for understanding the Moon's thermal history and for calibrating the crater counting techniques we use to estimate the ages of surfaces not just on the Moon but across the solar system. But the full scientific picture from Chang'e 6 is still being assembled. The analysis of 1.9 kilograms of material from one of the most scientifically important regions in the solar system will take years. Papers will emerge gradually, and each one will be evaluated by the global scientific community and incorporated into an ever-evolving understanding of lunar history. The 400-meter shift may eventually be explained in that literature. A paper might note that the actual landing site was chosen to maximize the probability of sampling a particular geological unit, or it might note that terrain assessment during descent identified a flatter and safer area, or it might not address the shift at all, because within the Chinese scientific community, the reasons may be considered obvious, or may be considered not appropriate for detailed public discussion. The history of space exploration is full of decisions that were made for complex combinations of technical, scientific, and political reasons, and that were publicly presented in simplified form or not explained at all. The Apollo 11 landing site was changed during final approach because Neil Armstrong could see that the planned touchdown point was in a boulder field. He overflew it manually and landed in a clearer area. That deviation was celebrated because it demonstrated the skill of the crew. The far side of the Moon does not have human crew members making visible real-time decisions. Everything that happens there is either pre-planned or executed by autonomous systems or commanded from the ground with a signal delay. And the reasons for those commands are internal to the mission control structure. What makes the Chang'e 6 situation distinctive is the combination of the strategic importance of the region, the confirmed existence of valuable resources nearby, the highly competitive geopolitical context of lunar exploration, and the complete absence of any official explanation for a measurable deviation from the planned landing site. Any one of those factors alone would make the deviation mildly interesting. All of them together make it something worth understanding carefully. Because this is not just about one mission. This is about the pattern of behavior that will characterize the lunar South Pole race over the next decade. Every mission will be watched. Every landing will be analyzed. Every data release will be scrutinized for what it includes and what it leaves out. And the decisions made now, about what to share and what to hold back, about where to land and why, about how to characterize findings, and whether to acknowledge complications, these decisions will shape the norms of behavior in the most contested region of the Moon. The permanently shadowed craters at the South Pole are billions of years old. They have been accumulating ice and volatile compounds since before complex life existed on Earth. They are a record of the early solar system, preserved in darkness and cold. And now, for the first time, they are within reach of human technology. Robotic missions are already operating in the region. Crewed missions will follow within a decade, and the decisions being made right now, the ones being announced and the ones being kept quiet, will determine how that access unfolds and who benefits from it. The 400-meter shift in the Chang'e 6 landing site is, in one sense, a small thing. It is a footnote in the technical record of a large and successful mission, but in another sense, it is a keyhole, a small opening through which you can glimpse something much larger, a competition that is intensifying, a resource that is strategically vital, a program that knows exactly what it is doing and chooses not to explain all of it, and a moon that is not the quiet, settled, well-understood place that 5 decades of distance had allowed us to assume it was. The moon is alive with possibility. It is covered in ancient secrets. Its south pole sits at the center of a geopolitical contest that will define the next era of space exploration. And somewhere in the darkness of Apollo crater, 400 meters from where it was supposed to be, a Chinese spacecraft collected 1.9 kilograms of the most scientifically valuable rock ever brought back to Earth. And nobody has said why it was there. That silence is telling us something. We just have to be willing to listen to it carefully enough. The next few years will bring more missions, more data, more decisions made in mission control rooms around the world about where to go and what to say about it. Some of what is found will be shared openly, some will not. The permanently shadowed craters will slowly give up their secrets, one landed spacecraft at a time. And the picture of what the South Pole actually contains, and what it is worth, and who is best positioned to use it, will become clearer and clearer. Until then, we watch. We analyze what is released. We note what is not released. We track the missions as they come, because each one is a chapter in a story that is only just beginning. A story about resources and power and science, and the oldest question in exploration, which is simply this: what is out there, and how do we get to it before someone else does? The moon is waiting. The South Pole is waiting. And the race to understand it and reach it and use it is the defining scientific and geopolitical contest of our era. One spacecraft, 400 meters off target, no explanation given. That is where we are right now. And where things go from here is something that everyone paying attention should want to watch very carefully.